So we just looked at the nearest neighbor classifier, right? So in the nearest neighbor classifier, we save the entire dataset in the so-called model. Before that, we looked at the handwritten digit 2 example where we simply created an average. And now let us look at something way more interesting, also more sophisticated, more powerful, also more complicated. This is the so-called linear classifier. And for the first time, what we will do is we will actually train these so-called learnable parameters. These learnable parameters are also called weights of our model, right? So in this case, we want to, let's say, create a so-called linear classifier to take in our data and then give us the prediction of what our data was. Let us say, again, because we have dealt with these images, that we want to create a model where we give these images, right? So we give these images X as input, and then we want as output the class. And let's say our images are of size 32 cross 32 cross 3, because these are 32 rows and 32 columns, and because it's an RGB image, it has these 3 channels, right, for the red, green and blue. So this is why it is our we have a volume here, and this is the input X to our model. So this X, and then we define a function. So this linear classifier is essentially our function, and with this function what we are doing is we are kind of transforming this image of size 32 cross 32 cross 3 to these 10 output numbers corresponding to the 10 classes that we are interested in. So our function will give us these 10 numbers, and we will get values like 0.1, 0.6, and let's say 0.05 and so on. And whichever number will be the maximum, we will say, oh, our image was probably of this class corresponding to the second index in this case. Okay, so I'll just drop this off. So again, what we are doing is we are giving as input X. These are our weights, yeah? We will talk about our weights in a bit. So these weights are the learnable parameters. We start with random values for weights, and then we find good values for this W. And as output, we will get these 10 numbers. So the output will be these 10 numbers. And what is X? X is of size 32 cross 32 cross 3. How much is 32 cross 32 cross 3? Well, 32 is 2 to the power 5 into 2 to the power 5 into 3. So 2 to the power 5 into 2 to the power 5 is 2 to the power 10. 1024 into 3 is 3072. So we have our input X as one long vector of size 3072. Yes, so this is essentially one long vector of size 3072. And then our weight is of size, what is our weight size of? Our weight is of size, let's see what it will come out to be. So we have this 3072 cross 1. What we want as output is a vector of size 10 cross 1, because we have 10 classes. Yes, so this we want as output. And here it's a linear classifier, which means we are just doing a matrix vector multiplication, and this W is our matrix W, right? So the matrix is called W. So what will the size of this matrix have to be to give us this output of 10 numbers? It has to be 10 cross 3072, meaning it has these 10 rows. So 1, 2, 3 all the way to 10. And it has all these different columns, right? It has 3072 columns, because each row then does a dot product with our image X and gives us the first value here. Yes, we will look a little bit deeper into that, but essentially what I want you to remember are the dimension. The W is of size what? We just looked at it. It's 10 cross 3072. Our input is of size 3072 cross 1, which is x, and our w is of size 10,3072, and then we also add this so-called bias, and the bias is always the size of output, and our output is of size 10 cross 1. And what is this bias? The bias is nothing but the offset from the origin. So if you think of, you know, this linear classifier, you can think of like just like lines in 2D, or these hyperplanes in a higher dimensional space. But when you visualize it, just think of it as lines, right? And when you think of it as lines, this bias is a single number which is just your offset from the origin. But we will look a little bit more deeper into this linear classifier in a bit. And then we will also do this as a take-home assignment. So what we are doing is, we are training, what we want to do is, we want to get to our output, right? So we often denote our output with y, and our y vector is of size, what is our y vector a size of? It is of size 10 cross 1, because we have 10 output classes. We know our size of input because our input is just the image flattened, yes? So our size of input, the x, is, we just wrote it here, it's 3072 cross 1. We have our weight vector, which is of size 10 cross 3072. We also have a bias here, right? And the bias is of size 10 cross 1. And this is the equation of our linear classifier. And what are the learnable parameters? So these are learnable parameters here, and the learnable parameters are also our bias. And we often ask a question, an interview question: how many learnable parameters? By the way, the linear classifier is exactly what the so-called fully connected layer or the dense layer in a neural network does, and we will look at that in a bit. But how many parameters in this model, how many parameters in that fully connected layer? It's simple. It is the number of the numbers that we have in our matrix and the bias. So how many numbers in our matrix? It's 3072 cross 10, which is 30720. And then how many in our bias? 10. So totally how many trainable parameters? 30730. So about 30,730 trainable parameters. Meaning we start with random for these, and then we find the correct value, the values that lead to the correct answer. Yeah, what is the correct answer? And we learn these values through our data, the data set that we created. So we will talk about how we train, but assume that we have somehow trained it, right? So once we have trained it, we will also do this interpretation. We will train it, and then we will interpret what we have trained. So what we are doing here is, we have our matrix W, right? What is the size? 10 cross 3072. Sizes are very important. This is why I'm repeating it so many times. So we take each of these rows. What is the size of each row? It is a vector of size 3072, a row vector. We take this and we reshape it. So for example, we take the first row and we reshape it and we visualize it. Yeah, and when we visualize it, it looks something like this. We take the last one here of size 3072 and we reshape it into 32 cross 3, and then we visualize it as an image, and it looks like this. And what is most interesting is to see what, say the horse looks like. If you look very closely, at least I can see like a two-headed horse. And this is what the model learned. So what it learned was a two-headed horse for my horse class, for my third last row, right? So when I visualize my third last row, it looks like this two-headed horse. And what does it mean? So when we do your matrix vector multiplication, yeah, let me drop this a little bit. Yeah. So when we do our matrix vector multiplication with say the horse class, so let's say this image is of a horse. Yeah. And we do, so when we are doing this vector matrix multiplication, we take this and multiply with this, we take this, multiply with this, and add all of them all the way till here, and then we get the value for our third last class here, right? And that is a single value that we get when we do a dot product of this. So when we do a vector matrix multiplication, you can also think of this as multiple dot products of this vector with all the rows of the matrix. And when we do a dot product of an image that looks like a horse with this image of this two-headed horse, which was learned in the third last row here, you can think of this as You can think of this as a classifier that we learned, right? So we then kind of find the similarity, yeah, the cosine distance in some sense. So this is another way to find similarity, the cosine distance. We looked at the L1 distance. We can now also think of this as a cosine distance that we find between our classifier and our vector, the input, the x. Yeah. And next we will look at how we train this. So this was just looking at what a classifier looks like. Then in this case it's a so-called linear classifier. Why linear? Because it's a linear operation in the matrix vector sense. All we are doing is wx, and we are then and then we also add a bias, and then that gives us the output, the y. Yes, and this is why it's called linear. And later, next, we will look at how to find good values for our w and b.